can't control my hair. So that's one way to keep it under wraps, I guess. Oh, so okay, Hugo has come online. Let's see if I can give him permission. No, can't give it to you either. Okay, so it seems like more people today than usual. I can't give permission to. I don't know why. While I'm waiting, let me go to OneNote and see if we can recover what we did last time. Would like to talk about our next exam and our previous exam. So I don't have results, but at least my calendar is clearing up finally. Okay, this has nothing to do with you guys. This has got to do with Black-Scholes stochastic differential equation, if you're curious. Before this came stuff from my other class. This looks like your class. Yeah, I think this is what we ended on last time, I believe. So we looked at this infinite Markov chain, having these probabilities as given. And this is an example of what's called a birth disaster or birth catastrophe chain, because you either go up by one, which is considered to be a birth, or you fall all the way back to zero, which is considered to be a catastrophe or a disaster. Okay, and what we did last time with this, I think I can recount it fairly quickly. We said that if you figured out the expected time to go from zero back to itself, that wasn't too hard because you could do it in one step. You could do it in 2 steps with 1/2 times a third, that's 1/6 probability. You can do it in 3 steps for the first time, 1, 2, and then this way.
Professor, I don't think you're sharing your screen.
Oh, just when you said it, I thought about it. It looks too good to me, but it doesn't look good to you. Okay, let me try it again. Doesn't do much good to recap something if you can't see it. Thank you. Appreciate you telling me. Okay, well, you haven't missed too much though. It's easy to recap. This is what I called before the birth disaster, birth catastrophe chain. You either go up by one or fall all the way back to zero. Turns out to have a structure that we can play with a little bit. Can you see the screen now? Let me make sure, because I see you, so I sort of assumed you can see me in the screen.
Yeah, we can see it now.
Okay, good, thanks. So we were trying to find the expected time it takes to first return to zero from zero without getting there before that last time. And you can do it in 1 step by going this way. You can do it in 2 steps by going up and down. That's the only way you could first return to zero in 2 steps. If you want to first return to zero in 3 steps, you have to go up, up, and then down. And if you multiply those probabilities, you'll get these fractions here. In order to figure out the average time it takes, you would just multiply the value of t0 times the probability it occurs. And if you do, you get this sum, which is the harmonic series, which means on average, it would take you an infinite amount of time to go from zero back to zero for the first time, which is really counterintuitive, especially since we had already established this. Rho 0, 0 is 1. Let's see if I can go back 1 page and just reflect on that a little bit. Yeah, we did this calculation on the earlier page. So here's the same Markov chain. And in order to figure out the probability of going from zero back to zero, we know you could do it in 1 step or 2 or 3. And it turns out that rho 0, 0 is the sum of all these probabilities, which end up looking like this, and you end up doing something like a sum of, so you get a series that looks like 1 over n times n plus 1. You can use partial fractions to figure out the a and the b, and it turns out to be cool. It turns out to be a telescoping series, which means most of the terms cancel each other except for the first and the last, but the last gets arbitrarily small, so the limit is 1. So this example is an example of a chain. Well, 0 is recurrent because of this. We've just shown that rho 0, 0 is 1. So, and since 0 goes to any other state by a past theorem, that means all the other states are recurrent as well. So this is a recurrent chain. And that makes the calculation that we first reviewed even more mystifying in a way, because we know the probability of getting back from 0 or getting back to 0 from itself for the first time takes on average an infinity number of steps. And yet we're assured that the chance of getting from 0 to 0 eventually is 1. So it seems somewhat paradoxical. But these things occur. And what I was saying at the very end, let's see if I did it here. Yeah, what I was saying down here is theorem 5 tells us that if you have a chain that's irreducible and under the proper conditions, its stationary distribution is 1 over mi. But in this case, and for I equals 0, pi 0 would be 1 over m0, and m0 would just figured out to be, well, we were doing it here, turns out to be infinite. So pi 0 is 0. And from there, it's not hard. Let me see if it's, yeah, I think what I told you is it turns out that that defines what is called null recurrent. So if the time it takes to get back to a state, a recurrent state, is infinite on average, then the state is called null recurrent. And it turns out that if one state is null recurrent in an irreducible state space, then all the states are null recurrent. And that would mean there's no stationary distribution, because that would mean that all the mi's here are infinite. So if you have a null recurrent state, that means there's no stationary. And the only salvation for this is to tell you that it turns out null recurrent states can only occur if you have an infinite number of state space. So all of this sort of counterintuitive stuff that's going on from last time happens only when you have an infinite number of states. It doesn't always happen when you have an infinite number of states, but it certainly could happen. So, so that's pretty much a recap. Any questions on it? This is pretty heady stuff. It's interesting because it involves calculus or analysis. It involves summing this series, which turns out to be a telescoping series, by converting it to that by partial fractions. And it solves the other series, which you have on the next slide. By recognizing it to be the harmonic series, which we know diverges. Questions on any of this stuff?
Professor, I have a question.
Sure.
Were you having trouble giving us permission to record?
For about 3 of you, yes. So are you asking for permission? Is this Hugo?
Yeah, if I mean, if it's possible, yeah.
Yeah, sure. I'm happy to try again. I was doing this more as my usual recap. So let me see if I can unshare this screen. And there's more of you here now anyway. So whoops. So let me see. Alejandro wasn't here before, I don't think. So let me see if I can give him permission. Nope, can't give him permission either. Hugo, yes, I can give you it. James, I don't know if he was here before, but I can give him it now. Great.
I got it. Thank you.
Welcome, Cassidy. I couldn't do it before and I still can't. Miles and Ricky, I guess I won't even try, but how about Sergio? I don't remember trying to give, yes, I can give Sergio permission. Unfortunately, you guys have all missed the review. But okay, is there anyone else? Okay. So, and we're further in. So let me pull away from this topic just for a second, because I want to talk about the upcoming midterm. So what do I need? It would be good to have this screen up again and maybe just advance it one. Let's see. Yes. I will come back to this topic shortly. So let me just turn the page, add a new page, and some lines on it. Okay. So with regard to the first midterm, I still don't have anything to return, but I can now tell you that the things that have been keeping me busy, quite busy, unfortunately, are now done. So that means I'm actually can turn my attention to your midterms and start grading them. So for me, that's good news. I know it's not good news for you because it's like 3 weeks later or whatever, but at least I can see the light at the end of the tunnel. But the other topic I need to talk about is your next midterm. And so I was thinking, let's see, today is the 25th. So let's put a little calendar on the board. We can. Oh, nope. Okay, so we're here Monday, the 25th. Monday, Wednesday, Fridays are the operative days for us. So the 25th is here, the 27th is here, the 29th is here, which means 30, 31. So the first is Monday again, is that right? 1, 3, and 5. So I was thinking that we'd have our midterm in this week here. That either the, make sure I got the calendar set up right. 30th, 31st, yeah, that's correct. It doesn't, at this point, worry me which day you choose, but one day of these three we should choose. So why don't we do that now? Before we take a straw poll just to see where the interest is there any reason to avoid one of these days over the others? So for what I'm asking is there could be some event going on campus that I don't know about. I know this is the day after Halloween, so if that's a day, if that's a day that you need to recover or something, then I suppose that's something to think about. But and then there may be personal reasons. Of course, you may have other midterms on some of these days, but those things usually cut both ways. You know, someone has a midterm on the 3rd, someone else has a midterm on the 1st, and they're trying to avoid those things. But I'm looking for more general issues that I may not know about. So does anyone know general issues of what's going on campus or with classes that would make one of these days a poor choice? Okay, I don't either. So, okay, anyone want to give a short pitch for one day or the other? It doesn't matter to me if you want to express yourself and you have feelings on that. Nope. Okay. So we don't have a lot of people wanting to talk about these days. So let me just ask you, let's take a poll and see how it goes. I'm just going to do this unofficially, just counting hands or something like that. So let me first get in a position where I can see everybody. Okay. So how many would prefer to have it a week from today, which would be the first? Nada, as I see it. I don't see anyone interested in having it the first. What about, oh, Hugo, are you speaking for the first or not? Not really. Yeah.
No.
No, okay. How about the third? Wednesday, the third. Anyone interested in that? I got one thumbs up from Ricky. And I've got another one from Isaiah. So I have two people indicating interest in the third. Okay, and unless everyone else is going to abstain, I don't think you're going to win. But let's see how it goes. Okay, so the last date was a Friday, which is the 5th. Indicate if that's your chosen date. Yeah, it's got at least 5, 6 people. Yeah. So okay, the issue is resolved. Let's go back. Now there are a few people who have me in both classes, and I'm going to go through this similar process with the other class, but I'm well aware that having 2 of my tests on the same day is not a good thing for anybody. So I'll try to make that so it doesn't happen. At least for you folks, unless you want it. I mean, there's like 2 or 3 people in both classes. If you really want to do it, that's your choice. But I think generally it's not a great idea. So let me go back and share the screen and make this official. Okay, so we have a test date, exam 2. Is November 5th. I need to get you a sample test, and I'll do that soon. We also need, after I give you the sample test, we also need to talk about time to go over the sample test, so a problem session. Obvious times that could work would be after class, which is when we have our office hour anyway. But in addition to that, I'm somewhat free on Tuesday and Thursday. I think I'm going to have some time actually at the university hour, which is not been the case the last several weeks. I've been involved at that time, but also at other hours. So in the afternoon on Tuesday or Thursday works. Morning could work as well. So let me get the test to you first, and then we'll worry about the sample test. I'm sorry, we'll worry about the problem session. Meanwhile, hopefully I'll be able to get your return your test before you take this one. Good. Let's move on. Any questions before moving on? I mean, the topic should be somewhat clear. Most of the stuff we've been doing since the first exam has been chapter 2. Okay, so let's go back and no. Okay, so this is the stuff we we're just talking about. Let's stay with it a little further. So what do we know about birth, death? Whoops. What do we know about birth disaster Markov chains? Well, we now know that there could be there's something called null recurrent state. So you could be recurrent and yet have the average time it takes to return be infinite. So I'll just, let me summarize this. So, go. So let's summarize some of what we know. So this is what we know so far about birth catastrophe. Markov chains. So we did problem 18 from chapter 1. And that one, it looked like this. The chance of going up was always P, was a constant there. And we're talking about an of states. That's what makes it interesting. And the chance of going down was 1 minus P. And in this case, we were able to show, we did this problem, we showed this chain is recurrent. And I'm just looking in the book real quickly to see if there's anything else we showed. Now that was the main conclusion. We showed it was recurrent. I think we also had a homework problem there, didn't we? Let me see. So again, I'm going back and looking at it. Yeah, I think we had a problem there. And I think homework was to show that the expected time it takes to go from 0 back to 0 for the first time is finite. That involves like a geometric series. And let's assume for the moment we did this. If we didn't do this, we could talk about it after class. But this would mean what? The state is recurrent from what we did before. And once we know that the expected time to get back to itself from 0 to itself is finite, then we would say this. And once we know that, this implies 0 is positive recurrent. Positive recurrent means that the expected time to go from one state from a state back to itself is finite. And that's more what we'd expect. Okay, and since it's irreducible, it turns out that once you know one state is positive recurrent, all states are positive recurrent. So this is an example of where all states, they're not only recurrent, which we already had from problem 18, but all states are positive recurrent. Okay. So let me call this Roman numeral 1, since it goes back to what we did in chapter 1, but it sort of extends it too. Then by theorem 5 from chapter 2, it's irreducible. Oh, by the way, feel free to correct me. This is all wrong. Where do the arrows go? I mean, the labeling is right partly, but the arrows are off. So this guy is a birth catastrophe, so it has to go from here to here, right? So maybe you're too polite. You didn't want to correct me. Maybe you didn't know. But either way, that's how this thing looks. It's a birth catastrophe chain, which means it goes up by 1 and or goes followed all the way back. Okay, I mean, the rest of the set is all correct. By theorem 5 says there exists a unique stationary distribution. Okay. So that's dealing with this guy. Roman numeral 2, the one that we dealt with last time we met, this guy. And this was a half. And this was what? 2/3. And this was 3/4, and so on. So the probabilities going up are no longer constant. This was a half as well. And the chance of going down here was 1/3. The chance of going down here was 1/4. Chance of going down here was, oh, this was what, 4/5. So this was 1/5, etc. Okay, so for that chain, which we just sort of reviewed, what do we know? All states are null recurrent. Which means by theorem 5 again, there does not exist a stationary distribution. Oh no, this is not letting me advance. And let's quite sure why. Let me put a line down here, maybe. Yeah, well, gave me a little bit of space, but not much. Let me see if I go back. Okay. I'm just curious if I leave this and then come back. That doesn't help very much either. All right, so I guess so here's the one I wanted to treat, but I'm having trouble fitting on the page. Let me see. Is there anyone who has a suggestion how I can scroll down? I mean, that's unusual. Usually it just lets me do it. Let me go away and come back and just see if I can get lucky. No. All right. Well, I'm going to go over to another page since I don't have much choice. So I'll add a page, put more lines on it. And let's talk about number 3. So Roman numeral 1 was recurrent. And I could even say positive recurrent. Roman numeral 2 was all null recurrent. And this means there was a unique stationary, and this means there wasn't one at all. And now Roman numeral 3, so let's just put down something like what we're doing here. So let's call this P0, P1, P2, and so on. 3. Infinite number of states. And so this would be 1 minus P0. And this one would be what? 1 minus P1. And this one would be 1 minus P2. And this would be 1 minus P3, etc. Okay, so this is the general scheme. Any birth catastrophe chain would have some probabilities going up and probabilities going down, and we're assuming there's no loop except maybe at 0. And what I'm trying to get to is we have a case where the chain is recurrent, and there's 2 types of recurrent now. Could be positive recurrent, could be null recurrent, and we have examples of both. In 1, we have a positive recurrent chain, and in 2, we have a null recurrent chain. And now for 3, what I'm asking for, I want an example. Where the birth catastrophe is transient. So what we're doing now from this example, we're realizing that if we're in infinite state space, it's no longer just whether it's recurrent or transient, which is what it has been up until now. The choice now is transient, positive recurrent, or null recurrent. And we have examples of where this birth catastrophe chain is positive recurrent and null recurrent. Do we have an example where it's transient? Well, there's sort of a trivial example. So let me see if someone can give me that. I'm looking for a trivial example where such a chain would be transient. Can you give me such an example? Well, actually, it doesn't have to be trivial. Can you give me an example, trivial or otherwise, where this chain is transient?
Can we just make it so the probability of PIs are all just 1?
Yeah.
Or that defeat the purpose of being a death catastrophe chain?
Well, okay. That's the trivial example that I was fishing for. So thank you. Who gave me that? Was that Ricky?
Ricky.
Yeah. So yeah, that's worth noting, even though it's not the most interesting one, but it's still worth noting. So what Ricky just suggested is, suppose the probabilities going up are always 1. then there would be no loop here because you're going up with 100% chance. And you're going down, well, that's part of the problem. If you're going up with probability 1, you're not going down at all, right? So why this is sort of the trivial example, because the probabilities of a catastrophe equals 0. So it's hard to really call it a birth catastrophe chain if you never have a catastrophe, right? You just keep going up and up. So, but I think this does do what I was asking. And so I'll give Ricky credit for that. All of the states would be transient because once you leave, not only do you not have a probability of 1 of coming back, you don't have any chance of coming back. Once you leave any state, you're on an infinite upward climb. Okay, so that's an example, but it's not quite what we're looking for. And the one that I'm looking for will be harder to find. So let me show you one. So here's a way to think of it. If it's going to be, so, and this is a little bit of fun, if it's going to be transient, then there has to be a way, let's just look at what's going on at 0. Then there has to be a way of leaving 0 and never getting back, right? Well, when you leave 0, you're not going to stay at this state very much. You're going to either go up or crash down. And that happens for every state past 0. So if you're really transient, the only way to leave and never come back would be to keep going up like this guy is doing. And what would be the probability of this? Well, if it's not all ones, the one that Ricky came up with, the probability of leaving and never come back. So the probability of leaving and not leaving 0, say, and not coming back should be positive. Should be greater than 0. Maybe I don't want to mess it up with this 0. So I'll just say should be positive. The probability of leaving 0 and not coming back should be a positive probability. Okay, so the only way to leave 0 and never come back is just to march off to infinity. Okay, and okay, I may have to reopen OneNote because it's not letting me scroll, which really is hampering me a little bit here. I'll play with this and then I'll reopen it and see what it gives. So what is the probability of leaving and not coming back? That would be P0 is the first step up. Then you'd have to multiply that by P1. And then multiply that by P2. And continue multiplying by the P's. How often? Infinitely often, right? Because if you don't continue to go up, then the only other thing that happens is you come back. And we're trying to find how it happens where you leave and never come back. And the only way in this diagram, with the arrows pointing the way they do, that you can leave and never come back is to march off to infinity along this top path. So you would need the product of all of these things to be what? Positive. Okay. Now, probably most of you, well, I don't know, I shouldn't say most of you, but at least a good number of you probably believe that this can't happen. Why? If the probabilities are not all one, if they're all ones, then it can happen. But if they're not all ones, then you're well, if they're proper fractions, you're multiplying a bunch of proper fractions together and you're getting something positive. And I guess I could just ask you, is that always true? Is that ever true? You know an example where you can multiply a lot of probabilities together and get something positive? Well, the easy example would be maybe one or two of these are like a half or a third or something, but the rest could be ones. In that case, it would be positive. But what if they were all less than one? What if all these probabilities were actual, we're not equal to one, we're less than one, so not this example. What happens when you multiply an infinite number of probabilities that are all less than one? Could that product be positive? What do you think?
Wouldn't the product be 0?
Yeah, doesn't that seem reasonable that it would be? Because if you multiply a half times a half times a half, that certainly goes down to 0. And in fact, that's a fact from undergraduate analysis, right? If you take any proper fraction like 2/3 or 3/4, so if you did that, two-thirds to the nth power goes to 0 as what? As n gets large. So any proper fraction, any proper fraction would go to 0. But then the question occurs, well, what if the fractions are not the same, but they're still proper? Would it still go to 0? What do you think? Ricky said he felt it would. Anyone else have an opinion on that? So here we're coming face to face with the question about, what do you know about infinite products? It may not be a lot. Okay. So, but let me not guess. I don't mean this to sound like a silly question, but it's really what I need to know. Do you know anything about infinite products of numbers? When it converges or not? Have you ever seen an infinite product? I'm not surprised if the answer is no. It's routinely not taught in calculus. It just doesn't come up. Where it could come up is in 3140 undergraduate analysis, but usually it doesn't come up there either, at least when I teach it. So my question here is really something to do with analysis. Is there an infinite product of proper fractions that doesn't go to 0? And the answer is there is. Okay. So Ricky, I'm sorry. I think your intuition is cool. I think it would have been my intuition as well. If all of these fractions are less than 1, how could their product, if they go on forever, be anything other than 0? But it turns out it can be. And now on that note, let me see if I can turn my OneNote on and off and just see if I can get this so I can actually scroll, because I'm not allowed to scroll down here for some reason. So I am going to shut this for now. Okay. And now I'm going to see if I can reopen OneNote. Okay. Well, that's promising. At least it gives me a little bit of swing down. Okay. So yeah, let me go with what I have here. Oh, you can't see it. My bad. So it's the same page we were on, but it's letting me scroll slightly down. So there's something, so let me see if you've ever seen it. There's something called Wallace's infinite product for pi. Let me see. Wallace's infinite product for pi. I should know about Wallace. He's a mathematician who lived, geez, let me see. Can I tell you anything about Wallace? He's not someone I know. I think he lived around Newton's time. I could be mistaken. I guess you can Google Wallace's infinite product for primes. And if you do so, this is what you get. It looks like this. So pi over 2 is equal to 2 2's up top, and then 2 4's, and then 2 6's, and then 2 8's, and so on. The pattern's clear. And on the bottom, you have a 1, and then 2 3's, and then 2 5's, and then 2 7's, and then 2 9's. And again, the pattern's clear. And well, that's Wallace's infinite product for pi over 2. Let's see. Well, has anyone seen this before? Okay, so if you haven't seen it before, how do you do infinite products? Well, you do them like infinite sums. You look at the partial for infinite sums. When you have something that goes, an from n equal 1 to infinity. Whoops, yeah. How do you get this? It's the limit as n gets large of something that looks like this. Now, let me call the index I. So I going from 1 to n of ai. So you define the infinite sum to be the limit of the finite sum. Well, this works the same way. You need a symbol for, well, this is capital sigma for sum. You need a symbol for multiplying a lot of numbers together, and the symbol that's usually used is capital pi. Be careful, capital pi and little pi look the same, and I'm sorry for that. So this is the pi that you know, the 3.14159, 3.14. Get it right, Rob. 3.14159. Etc. So that's this guy. But this one, let me make it look bigger. It's like capital sigma, it's capital pi. Pi is for P, and it's also for product in this case. And so what we're talking about is the product of a lot of terms, ai from I equal 1 to infinity. So there's a theory of infinite products, just like there's a theory of infinite sums. And in a sense, if you haven't seen it before, it's my honor to introduce you to it. Okay, and I'm happy to do so. Now, how would this go? How would you take an infinite sum? It's the same idea of how you take I'm sorry, how do you take an infinite product? It's the same idea of how you take an infinite sum. You take a finite sum and let the limit kick in. Okay, so this should be, if we define this analogous to this, it should be the product from 1 to n of ai, and then let the limit kick in. And when that happens, then you get the infinite product. Okay. Now, let's see how it works in this case. So if we just took the partial product, the first one would be 2 over 1. Because that's just the first factors here. And 2 over 1, of course, is 2. But if we take the second partial product, it would be 2 times 2, which is 4. And on the bottom, we'd have 3, which is 1 1/3. Okay. So this would be the product. This would be just one term by itself in this infinite product. And this would be 2 terms of itself. If we went to 3 terms, what would the third one be? It'd be 2 times 2 times 4, which is 16. And on the bottom, we'd have 1 times 3 times 3, which is 9. And what is that? That's 1 and what, 7/9? And I'll do a couple more since we're this far. So the next one would be 2 times 2 times 4 times 4. So that would be 16 times 4, which would be 64 upstairs. And on the bottom, it would be 9 times 5, which is 45. And so this is 1. And then you'd have to subtract 45 from 64. That's what, 19/45? Okay. So someone who has a calculator, this is our first partial product. Our second partial product is 1.3 and repeating. Our third partial product is is something like an infinite number of 7s and repeating. And this one I don't know. So somebody has a calculator. Well, I guess I have a calculator myself. I want to put it on. Yes. And what is 1? Actually, all I need is 19/45. So 19 divided by 45 is, all right, 1.4. I think I'm getting infinite number of 2s. Is that what you get?
Yes.
Okay. So that's going up to 4. Let's see how close that is to what we're claiming this to be. So if we take if we take pi and divide it by 2, which I could also do on my calculator. Just have to enter pi somehow. Yeah, I see it. And divide it by 2. It gives me 1.5708. I have it to that approximately. So this thing is approximately 1.5708. That's from the calculator. This isn't bad. It's getting closer. About one more. So what would you have upstairs? You'd had 64 before, 64 times 6, which I don't know offhand. That would be upstairs. And on the bottom, you'd have whatever you had before, which was 45. And now you'd have 45 times 5. Okay, so let's figure out what that thing is. And I've got the calculator in hand, so why not use it? 64 times 6. And divide that number by 45 times 5. And this time, I must have done it wrong. Try it again. 64 times 6 is 384. And divide that by, well, what is 5 times 45? That's just 225, right? Okay, so now I've gone higher. I'm 1.7 something. But it's not as big as this. It's 1.70666, that kind of thing. Okay, so you can see that this thing is slowly zeroing into this. Okay. I mean, a couple things come to mind. How did Wallace come up with this? Well, he actually came up with it from an integral, I think, involving trig functions. So here's a homework assignment. Homework. Explain why this holds. To be honest, I don't expect you to do it yourself just by looking at it, because then you'd have to explain everything that was in Wallace's head. I mean, it's possible, but I'm not trying to make this an impossible problem or hard problem. All I'm really asking you to do is look it up somewhere. So I'm sure if you looked up Wallace's infinite product of pi, it would give you this. And then let's see if there's a simple explanation of where this came from. I think there's a calculus explanation. Explain where this comes from. And I think the answer is calculus. But since none of you have seen it, at least look it up. Okay, now what does this have to do with what we're doing in here? Well, one thing we can do, once we know this product holds, we could, let's see. Yeah, we can write it a different way. We can write it as pi over 2 is equal to, we could multiply the 2's. You're just squaring 2's on 2's and 4's on top. 2 squared, 4 squared, 6 squared, 8 squared. That's all occurring upstairs. Because if you look at it, that's the pattern. And on the bottom, it looks like squares of 3 and 5 and 7 and 9, and then there's one out in front. Okay. Why don't we put the 1 here? And, well, maybe it makes sense to do the following. What does the bottom look like? Well, we could really just forget the 1, and 1 times anything is itself. So on the bottom, we have 3 squared, and 5 squared, and 7 squared, and 9 squared, and so on, forever. Okay. And if we take this infinite product, what happens if we divide it again by 2? So if we divide it by 2, on the left side, we'll have pi divided by 4. And on the right side, oh, what happened? It's very sad. 3 squared, 5 squared, 7 squared, 9 squared. And my dots disappeared on me. And if I divide this by half, then what do we have? Well, we have 1/2 times, group it this way, 2 squared over 3 squared, 4 squared over 5 squared, 6 squared over 7 squared, 8 squared over 9 squared. Dot. Okay, so now look at what's going on the right side. There's a proper fraction. It's positive between 0 and 1. Here's another proper fraction. It's 4/9. Here's another proper fraction. It's 16/25. Another proper fraction, 36 out of 49, 64 out of 81, and so it goes. They're all a product of a bunch of proper fractions. But their product is this, and this number is a probability, if you want it to be, but pi over 4 is less than 1. So this supplies what I was talking about before. Can you take a product of a lot of probabilities, infinitely many of them, and get something bigger than 1, assuming that these are all proper fractions? And the answer is yeah, if you believe Wallace's product formula, because I can think of this as P1 and P2 and P3 and P4 and so on. So I know I'm out of time, but I can at least make the picture I want to make. So here's the picture I want to make. No, I go to commercial. Okay, let me see if I can. Actually, I think OneNote is acting a little better now that I restarted it, but it also doesn't like me to be at the bottom of the page. So here's the picture I want you to consider. Here's 0. Here's 1. Here's 2. Here's 3. Let's have this probability be 1/2. And then this would be 1/2. And then this probability from here to here would be this 2 squared over 3 squared, which essentially is what, 4/9. And if that's 4/9, this would have to be what? 5/9. And then the chance of going from 2 to 3, let's have that be this, which is what, 16/25. And then the chance of going all the way back to 0 from here would have to be the complement, which would be what, 9/25. And you get the idea. I'm going to go one more. The next one from going 3 to 4 would be this probability, which would be what, 36 out of 49. And then the probability of collapsing or crashing would be 1 minus that, which would be what, 13 out of 49. And keep going. You know, these things keep going too. So from Wallace's product formula for pi over 2, we are now able to construct a birth-death chain. Whoops, a birth disaster chain, my bad, or birth catastrophe chain. where the probabilities going up are what are in these parentheses. And 1 minus that are the probabilities of having a disaster. Okay, now, what's the probability that you leave 0 and you never come back? The probability of leaving 0 and never come back would mean that you were 1/2 times 4/9 times 16/25 times 36/49. In other words, it's this infinite product here. So the probability that you leave 0 and never come back is this infinite product, because in this infinite product, you never collapse, you never crash, right? You always go up. And the probability of that happening is pi over 4, which is a little bit bigger, since pi is bigger than 3, is a little bit bigger than 3/4. So what am I saying? I'm saying in this birth disaster chain, there's an over 75% chance that you're going to leave 0 and never get back. In other words, you keep walking off to infinity. And the probability of that is this infinite product. Well, that means the probability of going from 0 back to 0 eventually will be less than 1, because over 75% of the time you never get back. So this would be an example where 0 is what? Transient. 0 is transient. Now, at this point, you might think, wow, this is really 1 in a million or something. But the answer is it's not. There are many infinite product of proper fractions that converge to something other than 0. So the rhetorical question over here, could you have an infinite product of probabilities strictly between 0 and 1, and their product is not converging to 0? And this is an example of one. And you can carry out this as far as you want, but I think we carried it out far enough to see that it's getting close to, it's between 142 and 17, which is where pi over 2 lives. Okay. So empirically, you can see this is happening. So this is like a 2-for-1 in my mind. I'm able to teach you something about a birth-death chain that you never would have thought of, and at the same time, teach you about taking limits of products, which is probably something that, well, from what you've been telling me, I don't think anyone has really seen this very much, if at all. Okay, so this completes the trifecta. We now have Roman numeral 3. We have now a birth disaster chain that is what? Transient. But if it's transient, it won't have any stationary distribution either. Why? Because, well, if you think of theorem 5, I'll give you a short explanation of why. If it had a stationary distribution, it would have to look like 1 over m0. That would be how the stationary distribution looks by theorem 5. m0 is the average time it takes you to go from 0 back to itself. But if you make the table for all the ways that you can go from 0 back to itself, let's see, that would be the time it takes to go back to here, given that you started somewhere else. And whatever the time, there are probabilities for all of these things. But down here on the list, there's a chance you won't get back at all. Not getting back at all is essentially saying that in this case, T0 is infinite, because the time it takes to get back to 0 never happens. And the chance of that happening is bigger than 3/4 by what we just said. So when you take the weighted average of this thing, whatever these things are, you're going to be multiplying infinity times a positive number. And that's going to give you a weighted average of what? Infinity. So this is going to look like 1 over infinity. So pi 0 will be 0. And that sort of conforms to what we already knew. We already knew from previous discussion that whenever you're at a transient state, the chance, there is no steady state there, or the chance of being there after a long period of time is 0. So 0 here is transient, but I claim all of these are transient. Why? Because they're all in the same equivalence class. And there's a result that says everything in the same equivalence class is either all transient or all recurrent. So since this one is transient, so are all the others. So what's the takeaway? There exists no stationary distribution. There does not exist a stationary distribution, which means there exists no steady state either. Well, I'm well over time. Look this thing up. And what I'm going to do next time, for anyone who's curious, I'm going to try to find the stationary distribution when it exists. So it won't exist in the transient case. It won't exist in the no recurrent state. So the only time it could exist is if we have a recurrent birth disaster chain. And that's what I'll do next time. Is this in the book? Unfortunately not. So you could find some of it online, but hopefully what I'm saying in class makes a little sense. So let me take my water break and come back for the office hours, where I'm happy to discuss any of this more. And I'll see you in about 15 seconds. Okay, I'm back. Any questions on what I did today? So if I had to recap it, is we did some of this last time. Problem 18 from chapter 1 dealt with the case when all the p's were equal. And in that case, the chain was recurrent, and it turns out to be positive recurrent. So we'll actually have a stationary distribution, which we haven't found yet, but we will. And then the example I did last time was an example where the states were no recurrent. So they were recurrent, but the average time it took to get back was infinite. And that's sort of new ground, because up until that time, we hadn't anything other than recurrent or transient. Now we have two kinds of recurrent, no recurrent and positive recurrent. The positive recurrent are nicer. They're behaving more the way we think they should. But the no recurrent are interesting, because the state is recurrent, which means you come back with probability 1. But the time it takes on average is infinite, which is really sort of paradoxical. And then here today, at the end, I showed you a birth to that disaster chain that is neither no recurrent or positive recurrent. This is an example, but it's not really a disaster chain because there's no probability of going back to 0. But using Wallace's product, we were able to come up with what? With an infinite product of things, and we were able to identify these to be the probabilities. And when you label the diagram this way, you actually get a birth disaster chain. And because from 0, never coming back, has a positive probability of pi over 4, which is a little bit bigger than 3/4 or 75%, that means zero is transient. Zero is transient means they're all transient. That means there doesn't exist a stationary distribution. And so this could happen too. And those are all the possibilities for the birth disaster chains. Any questions on that summary? Cool. Okay, so questions overall on anything? Today, last week?
For the transient state, is it only going to be ever that solutions are in the irrationals?
Oh, that's an interesting thing. So is it possible to have, you're asking, can you have an infinite product of proper fractions that's not irrational? Isn't that what you're asking?
Yeah.
I think you can, but I don't have one in my pocket, so I can't just show you that. Okay. So I don't think it has to be a rational number. So, but I'll think about that one. Yeah, but when you Google Wallace stuff, well, okay, here I think I don't have to think too hard. Let me think a little more here. Okay, you may not like this answer, but here's an answer. Take this part right here, right? And why don't we just divide it by pi? So what would you have then? You'd have 1/4 is 1/2 pi times the same product, right? Everything else the same, 4 squared over what, 5 squared, and so forth. So here you have an infinite product. Of course, I put the irrational number here, but technically speaking, you're asking me, does the product have to be irrational? And I'm saying, no, it doesn't. But now I've got my first fraction here being 1/2 pi, right?
Mm-hmm.
So that, I mean, that would, I don't think that's what you were looking for, but I don't know, maybe. It sort of makes you think that probably you don't have to have, I think we can come up with an example where where everything is rational. That is, the infinite product is rational, as well as the individual probabilities. But I don't have one right off the top of my head.
And it would still all be true that each of the, because each of the individual parts have to be less than 1, right?
Correct.
Okay.
Yeah, and that would be true here. Because each of these, it's clear less than 1, and this is less than 1 too. Any other questions? I think this is cool stuff if you've never seen it. So, I mean, your reaction could be, I guess here's what I might wonder. If you haven't seen infinite products before, I think your reaction could be positive or negative, I guess. Mine is sort of, oh, it's a cool thing. And I mean, and why not? I mean, if you could do infinite sums, why can't you do infinite products, right? So I just look at it as a topic that's sort of a whole in terms of what you've seen before. And so for me, I'm happy to talk about it if for no other reason, just to fill in that gap. But then it actually applies here to do something I'm interested in doing. I'm trying to come up with an example of a birth disaster chain that all the states are transient. And one way to do that is to find an infinite product along these arrows going up so that their infinite product is positive and still between 0 and 1. So there's a positive probability of leaving 0, never coming back. That makes it transient. So to me, it's a nice, nice connection where this actually connects to Markov chains kind of things. But I
so
mean,
oh,
go
sorry,
ahead.
for the pi example, wouldn't it just cancel out all of those terms just to be one? So it'd be like a half times one times one times one.
Oh, you mean up here?
Yeah, so if you were to like do the like 1 over 2 pi.
Yeah, so I'm not sure what you're asking.
If
You're,
you tried to like turn it into like the rationals, it would just become like a like the trivial kind of example multiplied by a couple of non-trivial starts.
not sure. I'm still say it again, James, one more time.
So what would happen is you'd have like a half and then like maybe like 3/4, and then at some point it would just be multiplied over and over again by 1.
Oh. That might be work. Let me think. Yeah, but if you're going to have ones, if you're going to have ones from some point on, does that mean you don't have the disaster? I'm looking at it as an example of the birth disaster chain.
I
So
mean,
then-
you would still have the birth disaster chain, but it would show that there's not like a subset of it that doesn't include like the trivial, kind of like birth catastrophe chain.
I guess I'm having trouble picturing all the ones. So you're telling me this product looks like proper fractions, but only a finite number of them, and then all the rest are ones? Is that what you're saying?
Yeah, so because to get like the 1 over 2 pi kind of solution, you'd have to take like the reciprocal of everything.
No, but I mean, why? I don't understand why this just can't be 1 over 2 pi here.
You're saying for just the probability of going from 0 to 1?
Correct. That would be my first transition. I mean, that's like 1/6 or roughly, because pi is roughly 3. So this would change.
Oh, okay.
You see what I'm saying? I'm
Mhm.
just thinking of this guy is my new one here.
Oh, okay.
And then all the others are just the same.
Hmm.
And in that case, what would it be saying? It would be saying there's a 1/4 chance of leaving and never coming back.
Okay.
So I think it's still, it fits what I wanted to fit. I wanted to fit this birth disaster chain. And I'm just having one of my probabilities be a little kinky in terms of what involving pi.
Okay.
Any other questions on this? I mean, if you get off on this, I will warn you, you have to be a little careful. I mean, it's good. It could be interesting for you, you know, assuming that some of you react in the following way. There's a theory of infinite products and what they converge to and how to find them and all the rest. It's almost like, oh, I don't know. It's like growing up around Disneyland and then finding there's a magic mountain or something, something like this. Or, you know, there's a different amusement park that has different events and different ways that it operates and so forth. And you may be interested in the other place as well. So you could get into, this is the tip of the iceberg, okay, because people are, you know, historically people did study infinite products, not as much as infinite sums. Infinite sums has the advantage of rolling into integration theory, right? So that's a big deal. Infinite products isn't that big a deal because it doesn't apply to integration theory that I know about, at least. But it is an area of calculus and analysis itself. So be warned. You might find it interesting, but to me that's a good thing. And on the other hand, if you don't find it that interesting, you don't have to worry about it for this class, because the main reason I wanted is just to come up with an example of a birth disaster where they're all, where the states are all transient. And so it lends itself for that pretty nicely. I don't think the explanation of Wallace's theorem, which is what I asked you to look up, I don't think that's an easy to see thing. I think it comes from calculus, as I said. I think it comes from integration formulas or something like that. But it's not like, you know, I don't think you can just stare at this and say, oh yeah, that's true. I mean, in a way, it's sort of an amazing theorem or result, because it's giving you a way to calculate pi in ways that are very different than the usual way. The usual way is dealing with the circle, right? And the definition of pi from the circle, and going back to the Greeks and all of the well-known formulas for the area and circumference of a circle. This is definitely analysis, because you're doing infinite products. That's a topic in analysis. But I don't have an intuitive feeling, like maybe there is, but I don't look at this and just say, oh yeah, that's pi over 2. Far from. In a way, I think the other day I gave you this one. I don't remember. I think we were doing sums, and I said 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. This one is pi squared over 6. Or if you like, it's the sum, whoops, the sum of what? 1 over n squared, where n goes from 1 to infinity. And this was first solved by Euler when he was a young man in his 20s, actually. And it made his reputation. And it had been unsolved for decades before then. So there's a whole history of this. So when you have these this is another one. This is a shocker for most people. If you add up the reciprocal of the squares, why would it involve pi at all, is the question. It doesn't, you don't see circles, you don't see pi, you don't see the usual places that pi occur in this thing. So that's another reason this became so significant. So to me, this is not that different, except I know the reasoning behind this. And if you ever get a chance to take history of math or some, actually they both have one thing in common. I think they both have trigonometry in common. So they're using trigonometric ways to get this, and there's trigonometric ways to get this, which maybe makes sense because trig is on a circle, the sines and cosines are on the circle as well, so that can give you the insight as to where pi is coming from somehow. It's coming from a trigonometric argument. But what I'm trying to say is, if you just look at this, or if you look at this one, both of them seem like magic, or seem like, wow, why? And that in part, that's why their names associated to these things. Whenever you have a mathematical result that people just never thought of, or don't see a reason why it should hold, but it does hold, that's reason enough to give credit to whoever came up with it. This is older than Euler's. I'm pretty sure of that. I don't know how old it is, but I'm guessing it's from the 1600s, if I had to guess. Maybe even earlier. This one is Euler's. No one had it before him. Wallace may have been discovered before by other people, by the way, if you like the history of this stuff, because there's so many civilizations that were doing things in math that, just because someone's name was on it doesn't mean he's the first necessarily. It's probably the first, in Europe. Probably. Any questions? Well, this may be a shorter day than for the office hour, I guess. Looks like a nice day too. Where I'm at, it's overcast and with rain on the ground. So I'll see you Wednesday.
Okay, see you Wednesday.
Yeah.